Hey everyone, and welcome to the fourth installment of AIME Improvement. I'm Derek Dong, and today I'm going to be talking about polynomials and complex numbers. So, just a brief rundown of complex numbers. So, essentially, complex numbers are, say, we have I, we introduce this new number I, and we call it the square root, or like we say the square root of -1 is I, sorry. And so I is a very special, it's not a variable, it's just a constant, it's like 1, except it's the square root of -1. And so what this enables us to do is let's say, okay, square root of 9 equals, say, square root of 9 times square root of -1 equals 3i, more or less. So now what we can do is we express these just like we have the real number line. We also have this complex plane because we can express numbers by a plus bi. So let me just draw this out. This represents a plus bi, and it's represented by the point A, B in the Cartesian plane. So the reason we need two numbers is because I doesn't really work too well with real numbers, so we need a separate number to distinguish it. So with this, you can notice that if this length is r and this angle is theta, then by trig, you have this height is r sine theta and this length is r cosine theta. So we actually have a plus bi equals, where by the Pythagorean theorem, r, since we go over a and go up b, r equals the square root of a squared plus b squared. So this is equal to r times cosine theta plus I sine theta, which we abbreviate as r cis theta. So that's notation. De Moivre's is a powerful theorem that basically lets us say r cis theta. Actually, I think it's actually explicitly written r1 cis theta 1, r2 cis theta 2. So we multiply two complex numbers. Then what happens is the magnitudes multiply and the angles add. So these theta 1 and theta 2, we call them arguments. Essentially, the way it works is from this positive real axis, we spin around some angle theta, and then that's what we get as theta. And it's counterclockwise by default. If you go clockwise, it's negative. So for example, 240 degrees would be approximately like here, and this would also be equal to -120 degrees as arguments. And you could also say, I don't know, like 600 degrees. That's not really too helpful usually. And in polynomials in general, there's a theorem called Vieta's. Well, it's like a formula. So it basically says if we write a polynomial as x, let's write it first as a0 plus a1x plus a2x squared is the standard way of writing general polynomials. We say that it's equal to an times, we factor it basically, and we know it has n roots because of the fundamental theorem of algebra extended. So essentially what Vieta said is an minus 1, so minus 1 to the 1, an minus 1 over an equals the sum of every root. And minus 1 to the 2, an minus 2 over an equals the sum of every possible product of two roots. -1 to the 3, an minus 3 over an equals the sum of every possible product of 3 roots. And so on and so forth until you get at the very end, -1 to the n, a0 over an is just the product of all the roots. So that's Vieta's. You can verify just by expanding out this thing. It's kind of gross, but if you want practice, you can check it out. So now that the exposition is basically done, let's talk about how to problem solve. So this is a pretty simple problem. We have z equals 9 plus bi, where b is positive real, and I is standard. And we know the imaginary parts of z squared and z cubed, imaginary part being just whatever's multiplied by I, are the same, and we want to find b. So if we just expand out z squared, we get 9 plus bi squared, and we get 81 minus b squared as the real part, and then we get 18bi just by binomial expansion. Z cubed is 9 plus bi cubed, and this equals 729 plus 3 times 81 times bi plus 3 times 9 times minus b squared, just b squared, because I squared is -1, and we have plus minus b cubed I, because I cubed is -1 times I is -I. And so the imaginary parts, setting them equal, is 18bi equals 243 bi minus b cubed I, implying that b cubed I equals 225 bi, canceling out the i's, canceling out the b's because b is not 0. Then we get b equals, it has to be plus or minus 15, but we know it's positive, so it's 15. So this is literally just taking the definition of a complex number of I, really. The second one actually has a neat trick. We have a greater than 0, and we have a polynomial with integer coefficients, such that this is true and this is true, a bunch of stuff equal to value, and a bunch of stuff equal to value. And we want to minimize a. So what we end up doing, clearly a is an integer, and so a neat trick that we have is if p of, let's say it like this, p of 1 minus a equals p of 3 minus a equals p of 5 minus a equals p of 7 minus a equals 0. So p of x minus a equals, we can factor out 1, 3, 5, and 7 because this is still a polynomial. We're just scaling by constant. So what we end up getting has the same roots. So like its roots are where p of x equals a. So we have x minus 1, x minus 3, x minus 5, x minus 7, and this is a ton of information. And we actually have some other polynomial here. We don't know about what's left. We do know that this is, actually, yeah, we don't know much about what's left. We just know that it has 1, 3, 5, 7 as roots, which means that if we add a to both sides, we get plus a here, which means plugging in p of 2, we get minus a equals 1 times minus 1 times minus 3 times minus 5 times q of 2 plus a, which means that minus 2a equals minus 15 q of 2. If we do this exact same thing for 4, 6, and 8, we get that this is equal to 9 q of 4 equals negative 15 q of 6 equals 105 q of 8. And so we know that since everything here is an integer, because q is an integer polynomial, then a has to be, 2a has to be like multiples of 15, 9, 15, and 105. So since 2 and all of these are relatively prime, then we know that the least common multiple of 15, 9, 15, and 105 actually divides a, which means that 315 divides a, so to minimize a, we take 315. So this is a very neat trick of just, if we have a bunch of values of the polynomial equal to a single thing, then we just subtract that constant and we get another polynomial that we know several roots about. This last one requires another neat trick. So let p be the product of the non-real roots of this, actually it would be of the non-real roots of this polynomial. We have, let's say, yeah, sure, p of x. I don't like how it's the same as this variable, but this is a function, it's a polynomial, this is just a variable. And we want floor of p. So we want the floor of the product of the non-real roots of this polynomial. So this seems kind of hard because we don't know what the roots are, but we can actually find what the roots are. In terms of if didn't have the non-real roots, if it said product of the roots, then it would be very easy. It would just be negative 2005 by Vietas. So I just wanted to point that out. Without it, though, we actually have that p of x is actually equal to x minus 1 to the 4 adjusted. X minus 1 to the 4 is this whole thing, but with a plus 1 instead of minus 2005. So we adjust for it by subtracting 2006. So where this equals 0, we have x minus 1 to the 4 equals 2006, which means that x minus 1 equals the fourth root of 2006 times one of these, either 1, negative 1, these are the obvious ones, but also I or minus I. You can verify that I to the 4 and minus I to the 4 are equal to 1, but they're just roots of unity. You can look what that is. You just go around the circle, divide the argument out, so on and so forth, which means that the non-real roots are where we ignore 1 and minus 1, and so x equals 1 plus fourth root of 2006 I. Let's say actually p equals this times 1 minus the fourth root of 2006 I. And by difference of squares, this equals 1 plus the square root of 2006. And so what we do from here is we say, okay, 2006 is between 44 squared and 45 squared. And so the floor of it equals 1 plus 44 equals 45. So in terms of tricks, this time there's not much. This is a big one. Again, subtracting out the constant that a bunch of values of the polynomial are equal to. And the other trick is noticing. This is very important. You have to notice a lot of common polynomials, normally like binomial expansions, but it could be other stuff. So you definitely want to look out for these sort of things. So that's all from me today for polynomials and complex numbers. Thanks for watching, everyone, and see you next time.